All right, welcome back. Now that we have talked about the different types of steps of radical electron pushing patterns that we're going to see this semester, let's dive into a specific reaction, which is in particular the halogenation of alkanes. And very specifically, we're going to talk about the chlorination of methane, which is a radical process. And as you recall from the last video, we know that we have three stages for each of these radical processes. We've got the initiation, we've got the propagation steps, and then the termination. And so starting here with the chlorination of methane, very specifically, we're taking methane, we are reacting it with chlorine, Cl2 gas. The only thing that we're going to do is we're going to add in light, so we can use like ultraviolet light. I forget the exact wavelength, but just use a certain light at one of these steps. And then we basically form a chloromethane where, we've put a chlorine group on the methane. And what's left over is basically hydrogen chloride, usually as a gas, but it's the same as hydrochloric acid. So, okay, so the first part is, again, the initiation step. This is where we're going to make our radicals that are going to do the reaction. The initiation step for the chlorination is just going to be the homolytic cleavage of the chlorine-chlorine bond. So we start with our Cl2, we shine a little light at it, and that creates our two radicals. So now we've gone from a non-radical reactant, we've formed our radical products, now we've initiated the reaction. In the propagation steps, this is where we have radicals now, and these reactions start with radicals and they end with radicals. So we just kind of move the electrons around. So what happens first is we are going to say that there is a hydrogen abstraction from the methane. So this hydrogen abstraction looks just like the pattern that we talked about in the previous lecture, where you're forming a new, in this case, chlorine hydrogen bond from the chlorine lone electron, along with one of the electrons from the carbon hydrogen bond. The other electron from the carbon hydrogen bond is going to stay behind on the carbon. So that's going to form this methyl radical here. So that forms our methyl radical and HCl gas. Now, the next thing that's going to happen is we have a halogen abstraction. So this methyl radical, of course, we're forming a new carbon-chlorine bond. That's the whole point here. So this is what it's going to do is the radical electron from the carbon is going to form a new carbon-chlorine bond by homolytically cleaving the chlorine-chlorine bond. So it takes one of those electrons, forms a new carbon-chlorine bond, and then also the other electron that was in this sigma bond is going to be left behind on the chlorine here. So basically that gives us our product, and it regenerates a chlorine radical. So now we've got our chlorine radical that can go through the process again. Okay, then we have the termination phase. Now the termination phase is going to be any of these following coupling reactions, right? We have three different radicals that we've talked about. We've got we only have two. So we have two different radicals. So we have three different possible couplings. You have a chlorine radical coupling with a chlorine radical that forms the chlorine gas, and so that just regenerates our starting material. Now you could also have the methyl radical reacting with the chlorine radical. That forms our product. That's a good kind of termination there. But we also have the methyl groups here, right? These methyl radicals that we just formed in the propagation step, these could just as easily collide. And when they do, they actually form ethane. Now, as you saw in the starting, in the start of this, we didn't have ethane listed as one of the products, right? This is like a waste product. But it is possible, you would agree with me, that we form this methyl radical. These methyl radicals can easily collide with one another, and they can form this ethane. So this ethane basically just becomes a waste product. That's something that we're going to talk about more as we get into the details of chlorination and more specifically bromination. So when we add up the propagation steps, we get basically, so we had our initial hydrogen abstraction plus the halogen abstraction. That was methane plus the chlorine radical, forming the methyl radical plus hydrogen chloride. And then the halogen abstraction takes the methyl radical plus the chlorine and then forms the chloromethane and the chlorine radical. You added everything together, cancel the methyl radical out, cancel the chlorine radical out. That gives you your net reaction, which is the methane plus chlorine forming the chloromethane and the hydrogen chloride. So note that this is what we call a chain reaction. I hope you kind of saw that during the propagation. Basically, um, we have this idea where we're regenerating, for example, the chlorine radical, and the chlorine radical is a reactant in one of the earlier steps. So that's kind of the idea with a chain reaction. So just kind of keep in mind these radical reactions tend to be chain reactions. So this was all nice when we kind of did it on the paper, except I kind of pointed out here at the end, there's nothing that's stopping these methyl radicals from joining with one another, coupling them with one another to produce ethane. Also, there's nothing that's really stopping these, like, for example, the halogen abstraction. So like you have this halogen abstraction that produces this chlorine. Well, this chlorine radical could then do a hydrogen abstraction on one of these hydrogens. So you're not going to necessarily stop with a monochlorination of the methane. And in fact, that's a problem, basically. You can imagine chlorinating the methane to get the chloromethane, then you could get dichloromethane, do it again, trichloromethane, finally tetrachloromethane. Down here we have the old words for this: methyl chloride, methylene chloride, chloroform, and then carbon tetrachloride. The way that we would name them, of course, using the IUPAC system, is chloromethane, dichloromethane, trichloromethane, and tetrachloromethane. So then if you're going to kind of play around with this and make sure that you actually get the monochlorinated product, you need to make sure that you use a high excess of methane compared to the amount of Cl2 that you use. Otherwise, you're going to end up with dichloro and chloroform, dichloromethane and chloroform as waste products. Okay, so so that kind of wraps that up. Now we're going to look at this mechanism again, but these mechanisms are kind of going to look the same as we go through the halogenation steps as we talk through it for the rest of this lecture. So make sure to take a look at the lecture activity down below as well to kind of get some practice with these steps. Okay, now there is a word here, radical initiator. It's exactly what it sounds like. It's something that initiates a radical reaction. And what it requires basically is it's got to have like a bond that can be easily cleaved homolytically. So in other words, producing radicals. And it usually uses heat or light to do it. And there's 3 different chlorines that we use. So we just saw dihalide chlorine. We saw that dichlorine can break in the presence of light and give you 2 chlorine radicals. The other thing that can happen is what's called an alkyl peroxide. So hydrogen peroxide, you may be familiar with that. That's H2O2. Alkyl peroxides are just any oxygen-oxygen bond, where those oxygens are then bonded to carbon groups. These can also easily homolytically cleave and give you 2 radicals. And then finally, the strongest initiator is what's called the acyl peroxide. So acyl group is basically just this, you have this carbonyl bonded to an oxygen, and then that oxygen is bonded further to another oxygen, which is bonded to its own carbonyl. It's almost like, you can imagine like 2 esters or 2 carboxylic acids, kind of clicking together and forming an oxygen-oxygen sigma bond here. And because this radical is so stable, this is actually the easiest one to initiate. And you can actually do it just at 80 degrees Celsius. So that's a really achievable temperature, right? You just need to boil some water and you'll be above that. Okay, so radical inhibitors, on the other hand, are exactly what it sounds like. These are compounds that are able to react with radicals and stop the chain reaction from propagating or even initiating in the first place. So stabilized radicals that are good for that there's 2 possible inhibitors. One is oxygen. So oxygen is kind of what prevents radical reactions from occurring in open air, and that's because oxygen can be written as a diradical. Here, let me write this out and hopefully it'll make more sense. This is not the O2 that you're used to drawing, right? You're used to drawing, oxygen, oxygen, double bond like that. Well, now we know that these bonds can homolytically cleave, right? So what if we took the pi bond and just took 1 electron from each of it, and that gave us this form of oxygen right here. So yeah, this diradical now can react with 2 other radicals possibly and shut down any radical reaction. Hydroquinone is another good one. Hydroquinone, basically we're going to look at it on the next slide, but it's got two very stable radicals. If you have a radical on this oxygen and on this oxygen, there's a whole other resonance form that kind of like stabilizes and allows these to be very, very stable radicals. So we'll look at that on the next slide, I believe. Hold on. Here we go. Yeah, so hydroquinone, if you do like a hydrogen abstraction from the hydroquinone, that gives you this radical here. You should notice right away, this radical is in the benzylic position. In other words, it's bonded directly to a carbon in the benzene ring. So we know that that's resonance stabilized, right? We can, we take this electron, we form a new pi bond from carbon to oxygen by breaking this pi bond, taking one of those electrons over here. That gives us a radical here. And then this radical is in an allylic position. We can move it around the ring, just like what we did with the benzylic radical before. Now, what if we did the hydrogen abstraction on the other side? That would give us another radical electron on the other side. Now, these two radical electrons are both in resonance such that they can form this extremely stable product, the benzoquinone. So real quick, let's just draw that mechanism here for benzoquinone. So I mentioned already, these are benzylic radicals. So that means that, you can take this electron and you're going to form a new pi bond by splitting up the electrons here on this pi bond that's in the, that it's in the allylic position of. Now this time what's going to happen, so we do that. This other electron though that's in this pi bond is going to form a new pi bond down here. And then the same exact thing happens on the other side, where now this oxygen radical is going to form a new pi bond between carbon and oxygen. Then the other pi electron is going to go down, it's going to form its own new bond between the bottom two carbons down here. And that gives you this benzoquinone here. So hydroquinone can be turned into benzoquinone just through hydrogen abstraction. And this is like an easy way to basically, you took basically two different radicals here, this R radical we didn't even talk about. This R radical took the hydrogen, now it's no longer a radical, it's just an alkane or whatever it happens to be. Same thing down here, we form another alkane down here. So like when you want to get rid of radicals, benzoquinone is a really good way to do that. Oxygen's less good. Oxygen tends to like chew up stuff, so you don't really get the products that you want, but hydroquinone, really good at that. Okay. All right, so now we're going to talk a little bit about thermodynamics, because what we really want to do is we want to be able to use these reactions in ways that are convenient to us in organic chemistry. We want to be able to predict the products of the reaction, and we need to be able to like determine, hey, if we do this reaction, what's going to happen? So in order to determine whether or not the process is favored, you got to figure out the delta G. Now, the good news is we have two different terms, right? We have the enthalpy term and we have the entropy term to consider. In these halogenation reactions, the entropy term ends up being negligible because you start with two molecules, you end with two molecules. And they tend to be gaseous, or if they're liquid, they're both liquid. So there's not really the change of phase in those either to worry about. So we don't even worry about the entropy term. We only have to worry about the enthalpy term. And we know that we can calculate the enthalpy term because we can calculate the enthalpy term by taking the, by comparing the bond dissociation energy that's required to break the bonds that are broken and compare it to the amount of energy that you get for the bonds that were made. So like, for example, here, like here we have carbon-hydrogen bond. Okay, we're gonna break apart a carbon-hydrogen bond. Here we have this halogen-halogen bond. We're gonna break apart that halogen-halogen bond for sure. And then we form two different bonds. We form a new carbon X bond and then a hydrogen X bond as well. So if we just have a small bond association energy tables, we can actually we can predict what it's gonna look like for each of them here. So to predict the enthalpy of the reaction, we can just use bond dissociation energies. And we know that we are going to take the sum of the bond dissociation energies for the bonds that were broken and subtract from it the bonds that formed. Like, so for example, this is going to be the same throughout each halogenation. We're going to talk briefly about fluorine and iodine, and then we'll talk mostly about chlorine and bromine here. So again, it's bonds broken minus bonds formed. So the bonds that are broken are always going to be these carbon-hydrogen and halogen-halogen bonds. And then the bonds formed are always the carbon-halogen and the hydrogen-halogen bonds here. So like, for example, for fluorine, for example, we're going to take the carbon-hydrogen bond, that's 435, plus the halogen-halogen bond, that's 159. We take that, add those two together, and then subtract from it the energy that we gain from the bonds formed, which is the carbon-halogen and the hydrogen fluorine, in this case, bonds. That's 456 and 569. So when we do that, we actually end up with a hugely exothermic reaction, negative 431 kilojoules per mole. And with chlorination, it's still exothermic overall, but it's less exothermic. That's negative 104 kilojoules per mole when we do that. With bromine, it's negative 33 kilojoules per mole. And then finally with iodine, that ends up actually being endothermic. It's plus 55 kilojoules per mole. So because fluorination is so exothermic, it actually happens too fast. It's too violent. You can't really stop with the monofluorinated product because you stick the fluorine in with the methane and it goes right away. You get just a total mess. It's not really a useful scenario unless, of course, you want to fluorinate everything. And that can be important. Like, for example, like Teflon is like something that's a hydrocarbon reactant plus fluorine, and it just fluorinates the whole thing. And that gives you that Teflon property. But so we're not going to be using it though in our practical reactions. Iodination, on the other hand, is endothermic, and so it's not really going to be thermodynamically favorable. So it's just not going to occur. So really we're going to focus on chlorine and bromine here in this class. So like looking at the different steps here. So remember, the first step is going to be the hydrogen abstraction. So we have both, we have the initiation step, right? That's where we take our chlorine and our bromine and we can split them apart with the homolytic bond cleavage. We're not going to take that into account. We're only going to look at the propagation steps. The first one is the hydrogen abstraction. For chlorine, it's actually exothermic at minus 21 kilojoules per mole. For bromine, it's endothermic, it's plus 42 kilojoules per mole. Now remember, the next one is the halogen abstraction. Halogen abstraction costs about the same. It's like negative 96 for kilojoules per mole for chlorine and negative 92 kilojoules per mole for bromine. So the net reaction ends up being more exothermic for chlorine and a little less exothermic for bromination. And also, real key point here is that the first step for bromination is endothermic, and that's gonna slow things down a lot. So basically, because the first step is a lot easier for chlorination, the activation energy for chlorination is a lot lower. In other words, it's going to go a lot faster. Bromination, on the other hand, is a lot slower, but because it's more slow, that means it's actually going to be more selective. We mentioned before that there's this issue when we chlorinate alkanes where the chlorine can just go to any position. And that's a problem. But with bromination, that's less likely to occur. The bromination is going to favor certain positions over others. Let's take a look at that. So, okay, so rather than methane, and ethane as well, just has two carbons in the same position. When we have propane, for example, it's possible that if we monohalogenate, so monochlorinate or monobrominate, we might get different results, right? We have two different positions of hydrogen atoms that could be abstracted here. We have two hydrogen atoms that are on the secondary carbon, and we have 6 hydrogen atoms that are on the primary carbons over here. So for propane, we get two possible halogenation products. When we use chlorine in this example, we end up with both products. And basically this chlorine, it's such an exothermic reaction that sometimes we get the 2-chloropropane and sometimes we get the 1-chloropropane. And so there's no real selectivity here with the chlorination. So because the secondary radicals are just slightly more stable than the primary radicals, the secondary halide is going to be the major product at 60%, and the primary halide is going to be the 40% product here, so it's a minor product. But that's still not really a good distribution, right? If we're doing organic chemistry reactions, like we want to have as high a percent yield as possible. And stomaching a 60% yield on a chlorination reaction kind of stinks. So here's a look at the energy diagrams here. because the activation energies are so similar between the hydrogen abstraction from a secondary radical versus a primary radical, even though the secondary radical is faster, the primary radical is fast enough that you do get this 1-chloropropane product. So that's something to keep in mind. Now, with bromine, on the other hand, when we brominate the same propane, we actually get a 97% selectivity for the secondary carbon. So this is what we call regioselectivity. This bromine is regioselective for the secondary carbon compared to the primary carbons here. And yeah, just 3% of that. So that's a really high percent yield. That's something that you can be kind of happy about when you're doing your organic chemistry. Now, in order to explain why that is, we need to actually figure out, by taking a closer look at the energy diagrams for both the chlorination of propane and the bromination of propane, and looking at the Hammond postulate. So brief review, remember the Hammond postulate tells us that the 2 points that are closer to each other on an energy diagram should look more alike. So if your transition state is closer in energy to your products than to your reactants, then you would expect those to be more similar, and vice versa. If it's closer in energy to your reactants, then the transition state should look more like the reactants. So here's our two different, right? So here we have our energy diagram for chlorination on the left and for bromination on the right. When we look at the chlorination, remember that's a low activation energy reaction. So that means that the transition state is going to look more like the reactants do. And the reactants are, this is our hydrogen abstractions phase. In the bromination phase, on the other hand, the reactants and transition state are really far away. The intermediate in this case, so the product of that hydrogen abstraction, is closer in energy to the transition state. So that's going to be what's really important. Oh, and I didn't mention this, but the hydrogen abstraction is our highest activation energy. This is our rate determining step. Okay, so as we mentioned, for chlorine, the transition state is closer in energy to the reactants. So what that means is, basically, it's like you have propane and chlorine, and that carbon-hydrogen bond has only started to break. And this chlorine-hydrogen bond is barely beginning to form. It's because they look a lot like the reactants here. On the other hand, when we look at the bromination is closer in energy to the intermediate, where we've broken that carbon-hydrogen bond. So now, this carbon-hydrogen bond is almost all the way broken in the transition state here. It looks more like the products than it does the reactants. So this is the key thing. The transition state for the bromination hydrogen abstraction, we've already almost broken this carbon-hydrogen bond. And we already know it's a lot easier to break the carbon-hydrogen bond on a secondary carbon compared to a primary carbon based on the bond association energies. On the other hand, the transition state for the chlorination hydrogen abstraction, it's barely broken at all. So there's not really been much of a difference here. We haven't had to put in that much energy to break this bond because it just hasn't broken yet. So this gives us a big difference in energy for the transition state of primary versus secondary versus tertiary radicals for bromination as compared to the chlorination. Remember, the chlorination, we haven't really broken that carbon-hydrogen bond, so they don't really look much different at the transition state for a primary, a secondary, or a tertiary radical. On the other hand, there's a huge gap in energy for bromination, where the tertiary radical is much easier to form than the secondary radical, and compared to the primary radical is the least likely to form. So bromination is going to be really useful for us because it's a way that we can predict which bromine product we're going to form, which brominated product we're going to form. We're going to form tertiary first, then secondary, then primary. So practically speaking, like bromination is going to be what we're going to use from here on out. Like for example, here we have 2-methylpropane. This 2-methylpropane contains a carbon-hydrogen bond on a tertiary carbon. Well, tertiary radicals are the most stable of the non-resonance stabilized radicals. So that means that bromination is essentially 100% at the tertiary radical site. You get almost none of the primary carbon radical. So on the other hand, the chlorination is not nearly as selective. It's more like 2/3 for the more substituted, the tertiary carbon, whereas it's still 35% for the primary carbon. That's not really a good distribution. We really want to be more towards 100% compared to like 2/3 and 1/3. So fluorination, we already mentioned this, it's the fastest process. So it just like, it doesn't really select for each primary, it's gonna fluorinate 1.2 of the secondary and 1.4 of the tertiary. That's why we don't really use it. Chlorine's intermediate, so it can be useful in certain scenarios where, for example, like maybe it doesn't matter which position you chlorinate, so you can just use chlorine. But bromination is really much more selective. You're gonna get the tertiary selective above the secondary and above the primary. So it's much more useful that we're going to be using bromination in this semester and next semester. Okay, so I know that was a lot. We've got some practice in the lecture activity below. Make sure you follow that. We're going to talk just briefly about some of the stereochemistry that comes up with it. Fortunately, it's not too complicated, but yeah, it is something to consider, that we need to consider. So this may be a good time to pause the video, but I kind of stuck these sections together here. Yeah, so talking about when we halogenate, so when we brominate or we chlorinate butane or something that's got a bunch of different carbons on it, we can form a new chiral center, right? Remember, a chiral center is a carbon that's bonded to 4 different things. So we're adding in a chlorine, and if we chlorinate butane, if we form the 2-chlorobutane, that forms a new chiral center. Of course, the 1-chlorobutane is not chiral, right? This carbon is bonded to 2 different hydrogens, so there's no chiral center here. Now, the chiral center here, it forms a racemic mixture. There's no stereoselectivity, as we would say, in this reaction. It doesn't select for the S or the R more. It's going to form a 50-50 mixture. It's just pure chance. There's no reason why it would form one over the other. Remember that whether we form an sp2 radical, so remember, if we have an allylic radical or a benzylic radical, that radical is going to be in a p orbital. Or if we have it in an sp3 orbital, our reaction can occur from either side. So there's not going to be a selectivity from above or from below here when we form our new product. So we're not going to end up with like an abundance of one or the other, S or R, stereoisomers. So just keep that in mind, that you get a racemic mixture. If we're like kind of drawing it out in like a normal way like we would, we don't just form 2-chloropropane, we form S2-chloropropane and R2-chloropropane in equal amounts. So it becomes a racemic mixture of those two. Okay, now again, if you took S3-methylhexane, you have a chiral center, which is, so we're starting with a chiral center here. So S3-methylhexane, we're gonna brominate it. Now, you might think that, oh, we're starting with an optically pure sample of the S3-methylhexane, so we probably get an optically pure product. That's not the case. Remember, the intermediate that we go through here makes this a radical. So we're going to have a radical here, and as we saw on the previous slide, those radicals can invert position. So we took something that was pure in the S configuration, and we just got rid of all of that by brominating it here. And so this chiral center will be a racemic mixture as well. It'll be a 50-50 mixture of R and S. So keep that in mind. Okay, all right, so that was some good review of halogenation. Again, throughout the rest of the semester, we're gonna focus on bromination most of the time, because bromination is the most selective, and therefore it's gonna be the most useful, because we're gonna be able to predict what products we make. So that does it for that, and we've got just one lecture video left in this chapter, just a couple more sections to clean up, and then we'll be done.